Okay. Let's see. Okay. Now, let me just go ahead and take this off. Okay, I hope everyone can hear me. So, in this live stream, we're going to be doing, what is it called? Rational functions. So, okay, hi guys. So, yeah, so we're going to be doing rational functions in this live stream that, you know, that's on here. And, of course, I don't think anybody will, actually join, but, yeah, this is just for education purposes only. And the reason why I'm doing a live stream, you guys, instead of a video, is because, with videos, I feel like there's just a lot to go over. And as of right now, I feel like I don't have as much time to be doing that. And of course, it's not that I don't want to show my face or anything. I'm right here. I'm just doing the, I'm gonna just be doing the problems on here. So, with that being said, we're gonna get started right away. And I hope everybody can hear me. Because, well, yeah, I want to make sure that everyone can hear me. So, the main idea about this, what is it called, about this section here, and it's the section, and it's in the description down below for the textbook that I used for this. And let me actually grab a charger because my laptop's about to die. So we're gonna be doing, we're just gonna be doing like everything about rational functions. I know it said intro, it does say intro, but we're gonna be doing everything about rational functions, or I'll at least try to go over everything. As far as graphing rational functions, we already did a video on how to do that. So we'll just skip that part. But the main idea is just understanding what the end behavior is of a rational function. Like, how do we find it? What does it mean? Because specifically with these types of functions, the end behavior is a little bit different than what we've been very used to. It's not that different. It just means, from the left and right, which I will go over that in just a second. But if you've seen my videos, if you've seen my videos lately on rational functions, you will find that we went over a few things. Number one, we went over, what was it called? We went over, oh gosh, we went over asymptotes. Basically what asymptotes were, right? That's the first thing that we went over. And this is just going to be a list of what we already covered. So, number two, so we went over asymptotes. That means like horizontal and vertical asymptotes. We went over what those were. We went over the parent function, parent, and I hope you guys can read that, parent function of a rational function. Okay, and my handwriting's not that great, by the way. I hope everybody can read that because, I mean, I really, really hope everyone can read that. What else did we go over? We went over and let me bring it a little bit closer so you guys can see a little bit better. And I'm using OBS Studios. If anybody could tell me exactly how to actually change the, what is it called? Because I really want to make sure this is very, I want to make sure that the video looks good. So, okay. Sorry guys, I'm just making sure the video is, I guess I'll figure it out later, but, yeah, so, basically we went over asymptotes, and then parent function or rational function. We then said, okay, well, we went over graphing a rational function. At least I think we did. If not, we can always do it again on here. I'll do my best to graph it. And then number 4, I think that was mostly it. I don't know if we went over rational equations. I don't think we did. No, we did not do that. So, I'm pretty sure all we went over was this and this, the top two, right? And let me grab oh, here it is, an eraser. So that's what we went over. So the main things I would like to cover, and I'll just save it like this because I don't know why. This is such a bad, like, it's literally on the floor. So forgive me guys for the loud sound that's on that there is. So, a rational function is, so basically, I'm going to try to go over the definition, and again, this is going to be from the book, and it's not that I don't know what a rational function is, I know what it is, because obviously, well, yeah, I know what it is. It's basically, so if you have a rational function, any rational function, so a rational function f of x is of the form, and then we have f of x equals g of x over h of x, such that h of x does not equal 0. Okay, now that is the most basic definition that I can give you guys off the top of my head. And we also learned what horizontal and vertical asymptotes are. So, when you look at a graph, and this is just very, very brief because I already went over this in another video. When you have a graph like this, you see that this is kind of how a rational function looks, right? And you're gonna look at, so basically, if let's just say that, okay, so let me redraw that. Hold on. I know on the last video when I drew these, I suck at drawing like the curves. So if we have something like this, and then something like this, right? We can say that this part here, this line, here, basically, and I hope y'all can see that, this vertical line here, it is called the vertical asymptote, okay? And it's x equals c, such that c is any real number, right? And I hope y'all can read that. I'm like, I know with this board I write really small, so yeah. So that is what a vertical asymptote is. Now a horizontal asymptote is the y portion, the y value that the graph looks like it's approaching. So for example, right here, when it's approaching from here, it looks like it's approaching this value here, this dashed line here, but it's not actually reaching it. Of course, you know, the way I'm sketching it, it looks like it is. Ooh, it almost fell off. The way that I'm sketching it, it looks like it is, but if you look at any kind of textbook or any kind of, you know, like online, even if you graph the function, or if you graph a rational function, you will see that the curves that look flat like this, whatever number that they look like they're approaching, they're not actually going to reach that number, okay? That is something that we have to remember about horizontal and vertical asymptotes, is that just because those values of horizontal and vertical asymptotes are like just because they're asymptotes, it doesn't mean that the graph actually ever touches them. So even though we do mark them on the graph, it doesn't mean that, oh, the graph, you know, touches those lines or those dashed lines. So that's basically what we went over in the last video. Now, there's a huge notation, like basically a whole definition about, you know, about what a rational function is, the form of a rational function, you know, all that good stuff. But you don't have to remember what that is. Like I said, the most basic definition that I could give you guys was to just say that it is a fractional function. So basically, like I said, f of x over g of x equals h of x, such that g of x does not equal 0. And I already said why. The reason why it cannot equal 0 is because if we have 1 over 0, that is undefined. So it cannot equal 0. Now, that is for any function. There are some exceptions as to some functions when you say, like, f of x equals 1 over x minus 3. this is, you know, the domain would be all real numbers such that x does not equal 3. Because if we have 1 over 3 minus 3, that's 1 over 0, that's undefined. And if we graph this function here, we are going to have a vertical asymptote at 3. So like this, right? And since, and I always forget this, so when you have a 1 over x minus 3, let me just go ahead and see it very quickly. This is the rule I always forget, you guys. So when you have when you have x to the n over x to the m, if n is less than m, the horizontal asymptote is y equals 0. Okay, that's what the main idea is there. And so so from there, that's why, you know, basically our horizontal asymptote would be kind of right here. Even though it's on the x-axis, you know, you could still kind of, like, just right next to it, you could say that the horizontal asymptote is y equals 0. So then you go ahead and you graph your function. If you look at, so basically if you have 1 over x minus 3, you can look at how the graph of 1 over x looks, right? And you can say, oh, 1 over x looks like this. This is exactly, and let me just kind of move it a little bit. This is exactly the kind of, what is it called? Shape that we want for our graph. So we're going to go ahead and draw a curve like this, and it doesn't have to be perfect, right? This is just sketching the function, right? It's just sketching the function. We're not really like graphing and doing all these types of calculations. I hope y'all can see that, by the way. It's like really, really difficult to like make sure that the camera gets all of this. Let me try to move it a little bit closer. Okay. Now, as for, so basically the domain is all real numbers such that x does not equal 3. Now the range for f of x equals 1 over x minus 3, that is going to be, let's see. So if our horizontal asymptote is 0, right, and that means that we cannot include 0 in the interval. So, or we cannot include 0 in our range, right? If we're just writing it as all real numbers, we can just go ahead and say the range is all real numbers such that y does not equal 0. Now, if they want you to write it in interval notation, you can literally do something like this. Now, this is going to be a little bit tricky because this is where we include the union symbol. You see, when you are doing rational functions and you're finding the domain of a rational function, this is something they teach you. I don't know, it depends on the school, but they do teach you this, I believe, in pre-calculus. At least that's how it was for me when I was in high school. Of course, in college algebra, they teach you the union symbol, but basically, this is what I mean. So when you have a union symbol, okay, this union symbol here just means that you are including two intervals. So they're kind of going together. If you look at the end behavior of this, or sorry, not the end behavior, if you look at the domain of this function, you can see that, oh, like it's what is it called? So basically, it goes from negative infinity, and we're looking at the x-axis from negative infinity to negative, or to positive 3, but we're not including positive 3, right? We know that, right? We know obviously it's from negative infinity, and let me make sure it actually catches this part, to positive 3, but if you just write that, it's not going to be right, you know? If I just say, oh, it's from negative infinity to positive 3, right? Okay. But what about this part? You know? We would leave that part out, so then we'll be like, okay, well, how do we write that? Like, you would ask yourself, if I wanted to include the 3 to infinity, how do I write that, right? This is where the union symbol comes into place, right? Or comes into play, rather. So we would say negative infinity to 3 union 3 to infinity, right? And we're not including 3 because 3 is not in our domain. If we plug in, again, like I said, if we plug in 3 for f of x equals 1 over x minus 3, the answer is going to be, or rather, we're going to get undefined. So that's why we're not including 3. We're putting a parentheses. Remember when I taught y'all, like, parentheses means that it's not included in the interval, okay? So that's one of the things that I really want to make sure that everybody understands. So let's erase this. Now, let's just say that we do not have to graph this function, or we do not have to graph the rational function, but it's still asking us, what would be the domain of this function, right? Or what would be, or actually not this function, but what would be the domain of a rational function without looking at the graph? If let's say we're taking a test, right? Or you're taking a test and there's a question that asks you, okay, well, what would be the domain of the rational function? And it's a no calculator allowed question, or calculator inactive, excuse me. So if we say, for example, find, and let me find the domain of, and not sure why it has, okay, so find the domain of f of x equals x minus 5 divided by x plus 4. And let's say that it doesn't want you to graph it, but it wants you to find the domain. Actually, let me just put domain and range. of f of x equals x minus 5 over x plus 4. And it doesn't want you to graph it. Of course, you can try to graph it, but it would take you a long time, right? You know, you don't want to do that, right? Give me a second, guys. Hold on. Sorry, guys. Hold on. Give me 1 second. Okay. Now, so to find the domain and range of this, again, there's a specific way to do this, okay? You can say that, for example, for any function, any rational function, whether it's, you know, even if I had like x plus 1 over x minus 5, x minus 2 over x minus 1, x minus 3 over x plus 4, unless it gives you a quadratic, then okay, that would be kind of difficult. But like unless there's a quadratic on the bottom where you can't really solve for x. But what is it called? So the domain and range of this, basically you just have to set it not equal to 0. So we can say that the domain is all real numbers such that, and this is the symbol for such that, at least that's how I write it, x plus 4 does not equal 0. Okay? That's how it would be. Now, all you have to do is solve for x. You subtract 4 on both sides, you get x equals negative 4, right? So then you say, okay, the domain is all real numbers such that x does not equal negative 4. You can leave it like that. However, sometimes your professor or your teacher wants to push you a little bit further and write this in interval notation. This is exactly how we did it in the other problem. All we do for this one, again, we're just gonna go ahead, and if you guys hear a blender in the background, yeah, ignore that. Anyways, so, okay, so we have this, right? And you don't have to graph it. Again, you really don't have to graph it, but this is just to help you understand how it would look. So obviously, our vertical asymptote is negative 4. And since it's a positive rational function, right, we would do it like that, and then we would just go ahead and, oh, and by the way, if x to the n, so if we have x to the m over x to the n and m equals n, then the horizontal asymptote will just be x over x, which is 1, right? Or any kind of value. If we have like again, this is how I taught it in the last video, right, guys? If we have 2x over 5x, so if we have 2x plus 1 over 5x minus 4, the horizontal asymptote is just 2/5. Y equals 2/5. So the horizontal asymptote for this function here, for the x minus 5 over x plus 4, is just going to be 1. Okay. So, we would have, so the horizontal asymptote would be y equals 1. So if we, so let me go ahead and do this again because I kind of messed it up a little bit. Of course, you don't have to graph it. This is just so I can show you guys. Obviously, the next example, we're going to do it without the graph. But I'm just showing you guys how it looks. So the horizontal asymptote is y equals 1, right? This is y equals 1. Horizontal asymptote is y equals 1. And we're gonna do, oh, and then the vertical asymptote is x equals -4, so we have something like this, right? So then we have something like this, and then this other part goes like this. You have to remember the basic sketch of a rational function. If not, you can go ahead and do a few points and then see, okay, you know, you'll obviously understand how it looks. You have to look at it multiple times. It has to be, the picture of a rational function or the graph of a rational function has to be ingrained in your memory. You have to look at it multiple times to understand it. That way, once you know how the basic parent function looks, whether it's 1 over x or -1 over x, then you can relate those to other functions as to how they would, as to the end behavior, how it would be and stuff, you know? Anyways, so the horizontal asymptote is y equals 1, okay? The range, as for the range, notice that because our horizontal asymptote is y equals 1, that means that the graph cannot touch y equals 1. We cannot make this equal to 1 because there would not be any solution, okay? It would be no solution for this if we make it equal to 1. Okay, but this is exactly like the domain. We're saying that the range is all real numbers such that y does not equal 1. So that means that in interval notation, we would have -∞ to 1, because it would go from, this is -∞, right? Then it would go up to this point, which is 1. It would not be included in the interval. So it'd be going like this, and then it would be coming back over here and going like this, right? It would be, so basically how it works, the rational function goes like this. It goes from here, and then it goes this way, and then it comes back over here and goes up this way. You see how it does not touch 1. So the range would be from -∞ all the way to +1, except we're not including 1 in the interval. That's why we're putting a parentheses. And then union 1 to infinity. It's going from 1 all the way to infinity, okay? That is how you find the domain and range of a rational function. Oh my goodness, guys, I'm so sorry. I need to put this up on the wall. It literally is such a nuisance. Okay. Let me just... Okay, this time we're gonna do one more of these, but we're not gonna use a graph, okay? That example was just for that purpose, okay? For the graph. We're not really gonna do that this next example. So yeah. For this next example, let's see. Let's just say let me use a different marker. I'm trying to think. X. Okay, find the domain and range. Right? F of x is x minus 7 over x minus 1. So basically, again, the domain, we can write this all real numbers. And remember, x minus 1 cannot equal 0. We're going to solve for 1, so x cannot equal 1. So that means it's all real numbers such that x does not equal 1. That means we're going to go from negative infinity to 1 parentheses, because we're not going to go, so basically negative infinity to 1, meaning that we're not including 1 in the interval, we're putting a parentheses. And then union 1 to infinity. Okay? That is the domain. Go ahead and box that. The range is going to be, trying to think. So remember that to find the horizontal asymptote, if we have x to the n over x to the m, and then n is less than m, or sorry, no, n is equal to m, excuse me. Then the horizontal asymptote is just a over b. That's if we have like y equals ax to the m over ax to the n, and m is equal to n, so sorry, bx to the n, excuse me, and then m equals n, so then the horizontal asymptote would just be a over b. Okay. I just wanted to make sure we understand that. So that means that because our powers are the same, our horizontal asymptote is just y equals 1. Okay. So that means that the range, because the horizontal asymptote is y equals 1, it's not going to touch 1 at the y-axis. That means that y equals 1 will not be included in the interval. So the range will be from negative infinity to 1, parentheses, because we're not including 1, union 1 to infinity, just like the domain. Okay. Oh gosh. Okay. So that would be, that is how we find domain and range of a rational function. Let's see what else. Oh, and end behavior. Okay. So there's a whole idea where, let's just say, and this is something that you go over in calculus as well, but we're not going to try to go so deep into it because for algebra we do not need to do that. So let's see. If we look at the function y equals 1 over x, and we want to find, you know, for example, we want to say find the end behavior as x approaches 0 from the right side. Okay. This is, I don't know if this is something that they teach you in algebra. Maybe they do. I know they teach you this in calculus. And maybe in pre-calculus. But, so if we have 1 over x, of course we can sketch it. You know, we can say that this is 1 over x. And like I said, any function, it doesn't matter what function it is. If it's even if it's like f of x equals x minus 3 over x plus 1, it doesn't matter. You can still do the exact same sketch. It really doesn't matter when you're doing these problems. You don't really have to waste your time having to graph the whole thing and then doing all of that stuff, because you really don't need to do that. So basically, as x approaches 0 from the right side, right? And the way that we would write this is x approaches this little, like, this signal, this right signal, this means approaches 0, and then we're going to put a little positive symbol, as our kind of like an exponent, but it's not really an exponent. It just means as x approaches 0 from the right side. As x approaches 0 from the right side, if we grab our pen and we go ahead and look at, it's approaching 0, but then it goes up, like this. So what happens to y as x approaches 0 from the right side? F of x approaches infinity. Okay? That means that as we go from 0, as x approaches 0, from the right side, f of x is getting bigger, and it's going up forever and ever and ever. It's going to go to infinity. Now, if we said as x approaches 0 from the left side, meaning that we're going to put a little negative symbol on the top here as like kind of like a, it's kind of like a power, but it's not a power. It's not an exponent. It is a it's just a superscript. I would just say that. It's just a symbol. It means that we're approaching 0 from the left. So this means that as we're going from here, and look at where my pen is, we're going to go to 0. As we go to 0, we're going down. So as x approaches 0 from the right, f of x approaches infinity. As x approaches 0 from the left, f of x approaches negative infinity. Okay, that is how you would write it. Some teachers want you to write it that way, others don't really care, but this is the notation that you would want to use when you are in pre-calculus. You don't use this, I don't know if you use this notation. In pre-calculus, you learn about the limit notation. This is college algebra, so we're not really going to do that yet. Okay. But that is what that means, right? That is how end behavior works. You can do this for any function. You can find the end behavior as x approaches 0 from the left or right. You know, and then they do a whole, I mean, I know they do a whole table, but you learn about that once you get to calculus, because they teach you that, about the whole table where you do like 0.1, 0.01, 0.001, etc. I was never really good at those in calculus. Or actually, like drawing those in calculus or forming, like doing it with a table. I actually hated doing those. But, anyways. So, yeah, so a rational function, I mean, the whole thing with the rational function, if you look here, you see how there's that notation of that whole crazy notation. That's kind of why I didn't want to write it that way, because it's, yeah. So, let's see. Oh, and one thing I wanted to teach you guys. I know that I don't know if they do this in college in algebra or not. I know they do it in college algebra. But when you have a rational function, any kind of function, like this, right? And really, this is y equals 0. This is a horizontal asymptote. One of the things that they would want to let you know, or one of the things that they teach you, is that so for example, if I have the following. Okay, if I have a rational function where what is it called? So for example, and this is the last thing I'm going to go over for this stream, only because it's getting kind of late, and I will go over rational equations tomorrow. But anyways, for example, if we have f of x equals x squared minus 25 over x minus 5, we can go ahead, obviously, and factor it and cancel it. So we have x plus 5 times x minus 5 all over x minus 5, right? We can cancel this out. We're left with x plus 5. So what does this mean, right? You're asking yourself, what does this mean? How does this affect our graph? Well, if we graph this function, being that x minus 5 is canceled out, we're going to have a line. We're going to say, just like when you did, just like when we graphed linear equations, you have so basically we would have, and I believe it would be, it would actually be, hold on. It would actually be right here. There would be an open dot there. So we're going to go down one, left one, down one, left one, down one, left one, down one, left one. So basically, it's going to look something like this. And it doesn't have to be perfect, but you see how there's a hole there? That is what we call a removable discontinuity. Okay? I will go over this more tomorrow because, well, yeah, I really just wanted to go over what the domain and range of a graph looks like and all that other stuff, but I will continue with this tomorrow. With that being said, guys, I want to thank everybody for watching. If anybody watches this afterwards, it's fine. But that is all for this stream. Obviously I don't want to keep it going because it's already getting kind of late. It's already 8:40 p.m. So I will continue this tomorrow. Please let me know, guys, if this was helpful. Please let me know if you could see the board. And I will see you guys in the next stream. Thank you so much for watching, guys.